Welcome to the class. In this video, we will discuss the applications of Beckman rearrangement. The first application of Beckman rearrangement is the synthesis of paracetamol. The synthesis of paracetamol through the Beckman rearrangement is a three-step process. The first step is the Friedel-Crafts acylation. We start with phenol as our raw material and we treat this phenol with acyl chloride in the presence of a Lewis acid catalyst like an FeCl3 or AlCl3. What happens in this reaction is an interaction of an acyl chloride with AlCl3, and that leads to the formation of an acylium ion or an acyl cation, which is CH3C double bond O+. Now this CH3C double bond O+ is a potential electrophile. It can attack the benzene ring at any of the carbon atoms of the benzene. Precisely which carbon atom will it attack depends upon the primary substituent which is already present on the benzene ring. In this case, the primary substituent has lone pair of electron, so therefore it is capable enough to donate its pair of electron to the phenyl ring. That means that this primary substituent is a ring activator because it activates the ring, and it is also an ortho-para director. Being an ortho-para director, it will attract the acyl cation that was formed earlier towards the ortho and the para position. However, attack at ortho position will be prevented because of the steric hindrance that is provided by the bulky OH group. Therefore, there will be a predominance of attack at the para position, leading to the formation of para-hydroxyacetophenone or 4-hydroxyacetophenone. The mechanism of this reaction is electrophilic aromatic substitution reaction, and if you want to know more about this, please refer to my video titled The Friedel-Crafts acylation. Step number 2. Conversion of ketone to ketoxime. If you look at the product of step 1, it is a ketone. A ketone which is flanked by alkyl group on one side and aryl group on the other. To convert this ketone to a ketoxime, all what you have to do is to react it with hydroxylamine in the presence of an acid which is used as a catalyst. This reaction involves the acid catalyzed nucleophilic addition, this is the nucleophile, nucleophilic addition of hydroxylamine to carbonyl carbon with the elimination of simple molecule of water. The result of this reaction is a ketoxime. The same reaction is discussed in the video titled The Synthesis of Oxime from Aldehyde and Ketone. Please do refer to it to know more about the mechanism. Step number 3 is the Beckman rearrangement. This is where actually the Beckman rearrangement takes place. The ketoxime is converted into N-substituted amide. And to convert the ketoxime into N-substituted amide, you just need to treat it with concentrated H2SO4. There are 3 key events in the reaction. The H+, the first event is that the H+ that dissociates from H2SO4, it goes and reduces the oxygen of the hydroxyl group. The second key event is the migration of the more electron donating substituent from the carbon of the oxime to the nitrogen of the oxime. In this case, the more electron donating substituent is para-hydroxyphenyl group. So this is what gets transferred to the nitrogen here. The third key event is the retainment of H+ back into the system, making acid only as a catalyst. The summation of these 3 events leads to the formation of N-substituted amide, which in this case is N4-hydroxyphenyl acetamide. N1234 4-hydroxyphenyl acetamide, which is also called as paracetamol. You may be familiar with the use of paracetamol. It is used as an antipyretic to bring down fever. It is also used in mild to moderate pain. It is used as an analgesic. Let us now look at the second importance of Beckman rearrangement. The second application of the Beckman rearrangement is the synthesis of caprolactam. Caprolactam is a 7-membered lactam or a 7-membered cyclic amide. And to make this 7-membered cyclic amide, in which nitrogen forms a part of the ring and is the first member of the ring, we need to start with a 6-membered cyclic oxime in which nitrogen is not a part of the ring. And to make this 6-membered cyclic oxime in which nitrogen is not a part of the ring, you need to start with a 6-membered cyclic ketone. For all obvious reasons, you have to start with cyclohexanone so that you get caprolactam, which is 7-membered cyclic amide. So the cyclohexanone is now treated with hydroxylamine in the presence of acid as catalyst. What happens here is acid catalyzed nucleophilic addition of hydroxylamine to this carbonyl carbon with the elimination of a simple molecule of water, and that results in the formation of a cyclic oxime. This cyclic oxime is now converted into 7-membered cyclic amide by just treating it with a strong mineral acid. There are 3 key events in the reaction. The first key event is the reduction of the oxygen of the oxime by H+ that dissociates from the mineral acid. The second key event is the rearrangement of electron pair from the carbon of the oxime to the nitrogen of the oxime, resulting in nitrogen becoming a part of the ring. The third key event is the retainment of H+ into the reaction system. The cumulative effect of these 3 events results in the formation of the 7-membered lactam or the 7-membered cyclic amide, which is otherwise here called as caprolactam. Uses of caprolactam. This is an open chain caprolactam. 1, 2, 3, 4, 5, 6, 7. It serves as a monomer unit in the polymer nylon 6. Nylon 6 is used in synthetic fibers and in plastics. Caprolactam is used as a precursor to 3 drugs: pentylene tetrazole, meptazinole, laurocapram. Pentylene tetrazole is used as a cardiac and respiratory stimulant. Meptazinole is used as an opioid analgesic, and laurocapram is used as a percutaneous enhancer. Laurocapram enhances the absorption of hydrophilic drug once it is applied before the hydrophilic drugs are applied over the skin. This is the application of Beckman rearrangement. I hope you have liked and understood the class. If it is helpful for you, please do not forget to hit like, share and subscribe. Thank you very much.